Hey everyone! So in this video I like to talk about solving equations. And so one of the main ways we draw conclusions with mathematics is by solving equations. And so we've had some exposure with equations, but I like to more formally state what an equation is and how we work with it. And so an equation is a statement which says that the expression on the left side of the equation, or on the left side of the equal sign, represents the same number as the expression on the right side of that equal sign. And so here are some examples of some equations. Maybe 10 plus 2 is equal to 5 plus 7, right? So there's an equal sign, an expression on the left and an expression on the right, and the equation's making this claim that the two expressions are coming out to the same number. And then here I can say 15 minus 10 is equal to 4 plus 3, right? This is another example of an equation. And then, maybe a more relevant example is something like x minus 3 is equal to 9 minus x. Right, so this is another equation example, but this time involving a variable. And so here, equations, one thing I like to point out is that equations can be true, they can also be false, or they could be neither. Right, so if we look at this first example here, notice that this left expression, that comes out to 12, right? 10 plus 2 is 12. And this right expression, well, that comes out to 12 as well. 5 plus 7 is 12. And so here, this left side does come out to the same value as the right side. This equation is true. And if we look at the second example, I've written out an equation. There's a left expression, there's a right expression, and in between them there's an equality sign. But if I look at the left expression, well, that comes out to 10, or not 10, that comes out to 5, right? 15 minus 10 is 5. And then the right expression, that comes out to 7, and 5 is not the same as 7. These aren't the same values. And so here, we have an equation written out. It's claiming that the two sides are equal, but really that's not true. This equation is false. And then in the last example, x minus 3 is equal to 9 minus x. Well, here, this kind of depends. Right, so it depends on the value of x. For some values of x, this equation is true, and for some values of x, this equation is false. Right, so here x represents some unknown number. Maybe I'll write this down. So here, in the last example, right, so here, x is some variable, and it represents some unknown number. And for some values of x, make the equation false. All right, for example, if I plugged in x is equal to, let's say, 8, right? So here I'd have 8 minus 3 on the left, that would give me 5, and then on the right I have 9 minus x, in this case 8, so 9 minus 8 would be 1, and 5 is not the same as 1. In this case, that equation would not be true, but sometimes the equation can be true. Some values of x make the equation true. Right, and so in this example here, that's the word for a value of our variable that makes the equation true. These are what we call solutions to the equation. And in this example, x is equal to 6 is a solution to the equation. If we go back up here and we plug in 6 for x everywhere we see that x variable, well, here on the left side, we would get 6 minus 3 is 3. On the right side, we would get 9 minus 6 is also 3. And the two sides would be equal to one another. And so here, x makes that statement true, makes the left side the same value as the right side. And so when we're worried about, when we're interested in the solutions to an equation, maybe we want to find the solutions to an equation. Now this is called solving an equation. So solving an equation means finding, I want to emphasize, all the solutions to the equation. Sometimes we'll deal with equations where there's only one solution. Sometimes we'll deal with equations where there's no solutions. And sometimes we'll deal with equations where there are many solutions. And really the goal with solving an equation is to find all of the solutions. So before we explore what it means or what it looks like to actually solve an equation, I'd just like to say that we can always test or check if a number is a solution to an equation. And we did this in one of the last examples, but I want to take a moment to really do it thoroughly for another. And so here I have the statement that says, is x is equal to 5 a solution to the equation 3x is equal to 16 minus x? And I definitely encourage you to pause the video and try this example yourself. And when you're ready, we can go through this together. And so here, what does it mean to check whether x is equal to 5 is a solution to this equation? Well, it just means that when we replace x with 5, wherever we see x, right? So here, this x is meant to represent the same value as this x, and we're saying, well, when we replace that with 5, do we get a true equation? Does the left side come out to the same value as the right side? And so here, here I'm going to replace x with 5, and I'm going to ask, does the left side come out to the same value as the right side? It's 16 minus 5. And another thing I'm going to do here is, sometimes it's just a good practice to, when you replace a variable by a number, wrap that number in parentheses. Sometimes if you don't, it can kind of lead to a little bit of confusion with what operations you're trying to perform. So I definitely recommend or encourage to wrap your numbers with parentheses when you replace them in for a variable. Okay, so here we have 3 times 5, and that's really denoted because there's no operation between our two numbers here. So 3 and 5, that's multiplied together gives us 15. And then on the right side, 16 minus 5. I know there's parentheses, but that's not multiplication. That's here we have subtraction as the operation between these two quantities. And that comes out to be 11. And so 15 is not equal to 11. This is not true. And so here, what that's really telling us is that no, maybe it's a good idea to write the conclusion to your result. So no, x is equal to 5 is not a solution to the equation. But here I definitely encourage you to plug in x is equal to 4 into this example, and you'll see that that truly is a solution. The left side does come out to the exact same value as the right side. So usually testing numbers by plugging them into your equation and checking if it makes the equation true, this is not really a great method for finding solutions. It's great to check your solutions if you have a solution in mind that you think is true. You can always test it by plugging it in, but it's not really a great way of finding or figuring out what the solutions to an equation are. And so really our main approach for finding solutions to an equation will be to perform the same action to both sides of the equation to turn the equation into a simpler one. And so what I mean by simpler one is, usually we'll sort of perform the same action to both sides of an equation, usually until we arrive at the equation, our variable, maybe it'll be x is equal to just some number. And then that'll be our solution, that'll tell us our solutions. And so here, maybe let me go over an explicit example of what I mean by this. So here I have the equation x minus 6 is equal to 11, and I want to solve this equation. In other words, I want to find the value of x that makes the left side come out to the same number as the right side of this equation. And you might be able to look at this equation and see right away that x is equal to 17 is the solution to this equation. It makes the left side the same as the right side. But I want to talk about an approach we can use to solve this equation that really extends to solving even more complicated equations that we might not be able to see the solutions to at a glance. And so let's go through that. So here the reasoning is that this left side and this right side, really they're there to represent the same number. We're looking for the value of x that makes the left side the same number as the right side, right? So if these are the same numbers, well, they should still be the same if I add on a number, right? So here, if I add 6 to this left side, that should be the same as adding 6 to this right side, right? If they were the same to begin with, if they represented the same number to begin with, they should still be the same number when I add on 6 to each of them. Well, here, if I have x minus 6 and then plus 6, well, minus 6 and then plus 6 isn't going to do anything. It's just going to leave me back with x. Right? Any number I take, if I subtract 6 from it and then I add 6, I'm going to be back where I started. And then on the right side, I have 17. Right, so here we see that the solution is x is equal to 17. That's the solution to our equation. And really, this is the general approach we're going to take to solving equations, is that we're going to try and perform operations to both sides of the equations to get that x variable alone, so that we can see exactly the value of that variable. And so here, maybe just to really confirm this, we can check, right? So we can always check our solutions, and this is generally good practice, right? So here, if I check our solution, x is equal to 17, what would I do? I would take that value and I'd plug it back into our original equation just to see if it makes that equation true. So here, if I replace x with 17, and I'm asking, I'm trying to verify if this is truly a solution. I'm checking if it makes the left side the same as the right side. So I'm going to put a question mark there because I'm verifying here. So 17 minus 6, that gives us 11. And that's the same as 11, right? So here we've confirmed that this truly is a solution. So let's take a look at another example here. Let's solve the equation now. Let's solve 10 is equal to x plus 8. And so we can kind of take the same line of reasoning, right? We're looking for the value of our variable that makes the left side come out to the same number as the right side. We're expecting these two quantities to be the same. And so if they're the same right now, then they should still be the same if I subtract away 8 from both sides. Right, so here, 10 minus 8 should be the same as x plus 8 minus 8 if 10 and x plus 8 were the same to begin with. Well, if I subtract away 8 from 10, that gives me 2. And well, if I take 8x and I add 8 onto it, and then I subtract 8 onto it, well, that's going to leave me with just that number x, whatever it is. And so here we're saying this only works if x is equal to the number 2. Right, so here, what have we done? We've subtracted 8 from both sides of this equation, and this choice of 8 was because we had 8 added on to x, and we wanted to get that x variable alone so we could see exactly what it is, what the value of this variable is. And so when we subtract 8 to both sides, well, we get rid of that plus 8, and we're just left with x. And so really, the practice that we're taking here is that we want to isolate the variable we're solving for. So we want to isolate the variable. And to do this, we perform actions. Maybe I'll space this out a little bit. We'll perform actions that are opposite of what we see happening to the variable. So in this example, we see that 8 is being added onto x, so we should subtract 8 from that expression. And really, when we do this, we want to do it to the other side as well, because if they were the same to begin with, then it's fair to subtract 8 from both sides and still call them the same. And so I'd just like to emphasize here that, here I'm saying we want to perform actions that are opposite of what we see happening to the variable. Here, these actions we want to perform, we really want to perform them to both sides of the equation. Right, so here, we took the left side of the equation and we subtracted 8 from it. We took the right side of the equation and we subtracted 8 from it, and that told us our solution to the equation, x is equal to 2. So here, let's do the same thing for these two equations, and again, I would encourage you to pause the video and try these examples out first. And then here, when you're ready, we can go through them together. So here it says solve 6h is equal to 42. So here, the operation or the action that's happening to our variable is this multiplication by 6. Right? So here, we see that 6h and 42, these represent the same quantity, and so if I take 6h and I divide that by 6, well, that should give us the same value as taking 42 and dividing by that 6. Right, if I take h and it's being multiplied by 6 and then divided by 6, well, that's going to leave me with the same number I started with, right? So here, this is just going to leave me with h. And then 42 divided by 6, well, that's just 7, right? 6 goes into 42 7 times. And so we see the solution to our equation is h is equal to 7. And this also works in reverse, right? Here we have division going on. We have x is equal to, or x over 3 is equal to 5. So we know that when we take our variable and we divide it by 3, we're getting 5. Well, if I multiply both sides of this equation by 3, so here if I take x over 3 and I multiply it by 3, well, that should be the same as multiplying 5 by 3, right? If x over 3 is the same as 5, then 3 times x over 3 is the same as 3 times 5. Well, taking x, dividing it by 3, and then multiplying it by 3 is just going to leave me back with x, right? For example, if x was 10, or maybe I'll pick another example. If x was 12 and I divided by 3, I would get 4. And then if I multiply by 3 again, I would get back 12, what I started with, just x. And so here, x divided by 3 multiplied by 3, that's the same as just x. And then on the right side, we get 15. So this tells us that 15 is the solution to our equation. X is equal to 15. And we could see that, right? If we plug this 15 back into our x variable, well, we get 15 divided by 3 is equal to 5, and the equation would be true. Now, one thing I want to mention also here is, we've spent a little bit of time talking about fractions and how we can work with fractions a little bit, but I just want to emphasize here, how do we multiply by 3 a little bit more explicitly? Well, right, we can write 3 as 3 over 1. This is multiplied by x over 3. And, well, that would give us 3 times x over 1 times 3. Right, when we multiply two fractions, we just multiply straight across. And then, well, here we can see that 3 is a factor of the numerator, 3 is a factor of the denominator. I can divide out that same factor from the top and the bottom and be left with an equivalent fraction. We just get x over 1, which is just x. And so this is kind of a long-winded approach to say the same thing we said earlier, but I just want to show all of the mathematics there that you can use to be very explicit with this computation. So here, let's take a look at one more example kind of in the same line. So here, I want to solve 4 over 5 times x is equal to 8. And here again, this is another example I think that would be a good idea to try yourself first. So how do we solve this equation? Well, here again, just like the above example, the first example above, we have multiplication here, and we can undo multiplication or reverse multiplication with division. Right, so here, if I take, 4 over 5 is just some number. If I take 4 over 5 and it's multiplied to x, well, if I divide by that number 4 over 5, well, this should be the same as taking 8 and dividing it by 4 over 5. If 4 over 5x is the same as 8 to begin with, right, dividing both of these quantities by 4 over 5 will give us, will amount to the same value. And so how do we divide by a fraction again? Well, when we multiply by a fraction, we just multiply straight across, numerator to numerator, denominator to denominator. To divide by a fraction, well, division is kind of like the opposite of multiplication, and how this is seen computationally is you multiply by the reciprocal of the second fraction. Right, so here maybe let's perform this computation here just to really show you how this works or what I mean. So first off, maybe I'll rewrite 8 as 8 over 1. I think it's easiest to see how fraction multiplication and fraction division works when both of the quantities are fractions. So I'm going to write 8 as 8 over 1, and this is being divided by 4 over 5. And so to divide fractions, we multiply by the reciprocal of the second fraction. And what does that mean? Well, that just means we essentially flip the numerator and the denominator of the second fraction. That's what the reciprocal means, is we switch the numerator and the denominator. So I still have 8 over 1 here. Nothing happens to this first quantity. But here, what I do is I take the reciprocal of my second fraction, switching the numerator, the denominator, and then I multiply instead of divide. That's what I mean by multiplication and division, or kind of the opposites. Is that here, where instead of dividing by 4 over 5, we're multiplying by 5 over 4. And we know how to multiply, right? We multiplied in the last example. We just multiply straight across. So this is 8 times 5, that's 40, over 1 times 4, that's 4. And so this is 10. Right, so here we're saying that 4 over 5 times x, and then we still have that division by 4 over 5. This is equal to 10. We computed that right-hand side. Well, here, if I have x and I multiply by 4 over 5 and then I divide by 4 over 5, well, multiplying by a number and then dividing by that same number, those undo each other, and I'm just left with x. So x is equal to 10. This is the solution to our equation. And here, I kind of went through that left side kind of quickly, and more generally just described how we can interpret that left-hand side. But maybe let's also do this, a little bit more explicitly so we can see how this works. Here we said that multiplying or dividing by 4 over 5 is the same as multiplying by 5 over 4. And so here, this step here of dividing by 4 over 5 to the left-hand side, that's really the same as taking 4 over 5 x and then multiplying it by 5 over 4. And so order of multiplication doesn't matter. I'm going to rewrite this, just to really show you how this works. I'm going to rewrite this as 4 over 5 times 5 over 4 times x. And notice that if we multiply out these fractions together first, we get 20 over 20 x, right? When I multiply fractions, I multiply numerator to numerator, denominator to denominator, and we get 4 times 5, 20, over 5 times 4, 20. And 20 over 20, that's the same as 1. And 1 times x, well, 1 times anything is just itself. We just get x. And so really that's just to show you that when we take 4 over 5 and we divide it by 5 over 4, or in other words, or when we divide it by 4 over 5, in other words, multiply it by 5 over 4, those cancel out and we're just left with just our x variable here. And so in general, if you want to get rid of multiplication here of a fraction, you can multiply by the reciprocal of that fraction. You could have, instead of just dividing by 4 over 5, we could have gone directly to just saying, let's multiply by 5 over 4. That's really what we did. Okay, so hopefully that wasn't too confusing. I know fractions can get a little messy. I just wanted to be very thorough in this and show you, all the different ways you can kind of think about this. Actually, let me say one last way. We've also talked about how multiplying by a fraction is the same as multiplying by the numerator and then dividing by the denominator. Maybe I'll write this out one last time. So here, if we solve 4 over 5, x is equal to 8. This is really saying multiply x by 4, divide it by 5, and then that's going to give us 8. And so we can kind of take these little operations or actions one step at a time and individually. And so here I can undo this multiplication by 4 over 5. I can undo it by first multiplying by 5 to both sides to undo this division by 5. Right, so here if I multiply both sides by 5, we can kind of see that this would give us, if I write this out as 5 over 1 times 4 over 5, x is equal to, on the right side we get 40. Well here, this would give us 20 over 5, x is equal to 40, which is the same as, well, this is equal to 20 divided by 5 is just 4. 4x is equal to 40. And then we can undo this multiplication that came from the numerator of our fraction. We can undo it by dividing both sides by 5, or by 4, right? So here if I divide, oops, I left out a 0 here. If I divide both sides by 4, well here, taking x, multiplying it by 4, and then dividing it by 4 is going to give us x. And then taking 40 and dividing it by 4 is going to give us 10. So we get the same result either way. And so here, right, so earlier we got x is equal to 10. So this is all to say that here, multiplying by a fraction, if we want to undo that multiplication, we can divide that fraction from both sides, which is the same as multiplying by the reciprocal of that fraction. So we can multiply by the reciprocal to both sides. Or we can sort of take the fraction one step at a time, numerator and denominator separately, and we can undo the division of 5 with multiplication by 5, and we can undo the multiplication of 4 with division by 4. So this is just to get you a little bit more comfortable with fractions. So hopefully this was helpful, but if not, I wouldn't dwell too much on it. We'll get some more exposure to fractions all throughout this course. So I have two more examples I'd like to share with you that are a little bit more applied. So this first example says that Jan's bank account earns 5% interest each year. So what does this mean? Now this means that at the end of the year, we take 5% of how much she has in the bank, and then that's getting added on to her amount in the bank. So she's gaining more money at the end of every year. And so it says that her account earned $42.50 last year. So this was 5% of her bank account amount that she's getting added on to the amount in her bank. And so it says, what was her balance at the beginning of the year? So we don't know this amount. We don't know her balance at the beginning of the year. So maybe let's label this with the variable b. b represents beginning balance. And so what we're saying is that if we take this beginning balance and we take 5% of it, in other words, multiply by 0.05, well, this is going to be the amount that she adds on to her bank account. And it's told to us that that's $42.50. Right? This was the amount that she earned from interest that last year. And so this should be equal to $42.50. And so we want to figure out what her beginning balance was. We want to figure out what the value of this variable b was. And so we need to solve this equation. And so to figure out this value of b, we want to undo this multiplication of 0.05. Right? So notice that if these two quantities are the same to begin with, if we divide them each by 0.05, we should still end up with the same quantity, the same value on the left as on the right. And so here, when we divide this left side by 0.05, that's going to undo the multiplication by 0.05, and we're just going to be left with b. Now on the right side, here we can do this with the calculator. We can divide 4250 by 0.05, and this gives us $850. And so what's the conclusion? Is that Jan's balance at the beginning of the year was $850. And so here, Jan earned 5% interest on her $850 that was just sitting there. So here this just shows you that interest is a powerful way of getting money. You know, she had $850 to start with. Sitting there, she earned 5% back, $42.50 just for having the money. So in this next problem, it says that a roll of carpet contains 400 square feet of carpet. And if the roll is 16 feet wide, how long is the roll? And so here, right, we want to figure out the value of how long this roll is. So let's give this unknown value the variable L. Let's say L is the length of the roll of carpet. And so here, you know, maybe just have a picture in mind. You know, this carpet, it's a rectangular carpet. It's rolled up, and if we unroll it, you know, it'll kind of come out long and flat. And one side, we're saying, is 16 feet wide. We know this from the problem statement. But the side that we don't know is what we're calling L. And so here we're told that the area of this carpet is 400 square feet. Well, what's the value of L then? Here we can use an equation to figure that out. We know that if we take 16 and we multiply it with L, we get the area of the carpet, which we're told is 400. And so here, if we want to get L alone, if we want to isolate L, we ought to divide both sides by 16 to undo that multiplication to L. And so to divide 16 from the left side of this equation means that we ought to divide 16 from the right side of this equation as well. If 16 times L is really the same value as 400, well, 16 times L divided by 16 is the same as 400 divided by 16. And you know, if we multiply by 16 and divide by 16, that undoes one another, and we're just left with L, the value we're interested in, and that's equal to 400 over 16. And now, you know, we can use the calculator, but maybe for this example, let's avoid it and let's try and figure this out without a calculator. If we have a fraction, we can always reduce the fraction by dividing the same quantity from the numerator and the denominator. And here I see both of these quantities, they're even, but even more than that, they're both divisible by 4. So let me divide out 4 from the top and the bottom, and we'll be left with the same, an equivalent fraction. So 400 divided by 4 is 100. Right? If I split up 400 4 ways, or into 4 groups, each group has 100 in it. And then 16 divided by 4, well, that's 4. And then actually I notice I can still reduce this fraction even more. I can divide 4 from the top and bottom again. Right? I know that 4 is divisible by 4 and 100 is divisible by 4. Well, you know, how do I split 100 up into 4 even parts? Well, 100 split up by 4 is 25. Right? You know, you can kind of think about quarters and dollars, right? 25 cents, 4 of those goes into $1, 100 cents. And so 100 divided by 4 is 25. And so here, our fraction is the same as 25 over 1, and anything divided by 1 is just itself. So this is 25. L is equal to 25. Maybe I'll label it with feet. And so here, maybe just to really state the conclusion of our work is that, the carpet is 25 feet long. Well, and I guess one thing I should mention, just to continue on this rant about getting more comfortable with fractions, here we saw that we kind of took 2 steps to divide out this fraction. Right, to divide the numerator by the denominator. And that's okay. Right? Here, you might not see the big step you need to take to compute your result all in one. Sometimes it's okay to do it in steps. And here we saw it that dividing out by 4 and then dividing by 4 again was an easier way to really see how to compute this, or this 400 divided by 16.